Structure used for linked representation is linked list. So one thing that needs to be concentrated or should be considered in case of linear and linked representation is all the data items. When you take the linear representation, the data items are side by side. Data 1 will be here, data 2 will be here, data 3 will be immediately after that, and so on. Data n will be at the end. This is linear representation. In linked representation, the data items will be spread across the entire memory. Suppose if first data item is here, second maybe here, somewhere here, third maybe somewhere here. So like this, the data items are spread across the memory. So when the data items are side by side, you can access the data items one after the other using the index. I can use the index. Maybe the index starts from 0 or 1 or whatever it is, but because the data items are side by side, you can use the index starting from some given starting value, most probably 0. Then the remaining 0, 1, 2, 3, and so on, you can take the index and access the items. But the same thing is not possible here because the data items are not at one place, they are spread across the multiple places of the memory. But the advantage of this linked representation is wherever there is a free space that can be utilized. So that is the reason why normally linked list is preferred over linear list. But the problem with linked list is, so if I want to reach from one data item to the other data item, in addition to the data, I require one more field, one more component to go to the next item, which we generally call it as link. So in linked list, every data item not only contains the data, but also link to the next data item. Otherwise, it is not possible to access. So from first data item, there may be a link. From there, will using that link will be reaching second data item. From second data item, there will be a link to third, and so on. This is how it should be. So here the important thing to note is, if I take every data item in linear representation, every data item in linear representation will just contain data, because I don't require any other thing to access because they are side by side. I can just use the index to access it. But in linked representation, every data item is not just containing the data, but also some link or pointer to the next data item. So one additional component is required to store the data and to access the data. So this is how the linked lists are represented. So one extra field, this link field here in normally in C language, is a pointer, because pointer will be having the address. So pointer will be holding the address, and pointer when you store the address, it will be giving you the address of the next item. You can use that and go there. That's how we can run through the different data items of the linked list. So one extra field is required, pointer field, but that is not required in linear representation. So that extra field surely will consume more memory, but the advantage of linked list is we need not have consecutive memory area. Wherever some small part of the memory is available, we can utilize and proceed. So generally linked lists are preferred. One reason is the utilization of memory is good. Second reason is the insertions and deletions will be efficient in linked list, because in case of linear list, there will be a lot of movement takes place when you want to insert or delete. But in linked list, just change in links will allow the insertion and deletion. So the insertions and deletions are efficient in case of linked representation. So when you take the node, generally the data item, whatever I'm referring, generally we call it as a node. So there will be a node in a linked list. That node consists of data and link field, and like that there will be nodes present. there will be series of nodes present. So generally, even though in memory the linked list is like this, this is how in memory it is present. So the nodes are present like this, but for convenient of representation, we can represent linked list like this. But in realistic terms, the linked list will not be like this. Linked list will be like this. But for our convenient of understanding, we can write all the nodes one after the other, and we can have from first node there will be a link to the next node, there will be data of second node, there will be link, and so on. It will proceed until we reach the last node. So when you take the last node does not have any further node to refer. So it is the link field of the last node will be represented with null to indicate that there is no further node present. So this is how the linked list is represented to hold any data structure. And one more thing to note is always we should have pointer to the first node. I may name it as first, I may name it as start, I may name it as head, whatever it is, but there should be pointer to the first node. So in program, we'll be just holding the address of the first node. Once we have the address of the first node, we can traverse through the entire linked list by using the that address, because address of the first node will give this and you can access the data. Then the link of the first node will fetch you the address of second node and you can proceed further. This is how the linked lists are represented. Whatever may be the language, the representation remains same, but in C language that link part is a pointer. In other languages, suppose if you take Java, the link part will be reference, but in C language, the link part is a pointer. Now, when I take this is how the node is represented. But in C, if I want to represent a node, because there are mix of data items present, normally uh, if I take normal linear representation, there will be just data present. So I can use a simple array, but here there is a mix of data items. Generally, they are heterogeneous data items. So we use structure to define the node of a linked list. So struct means struct is the keyword. So we use structure to represent the node in C language, to represent node in C language. So when I take struct, the example, for example, if I take here, I can take some example struct. I can say struct node. Here the data part generally we keep integer, but it can be anything by itself. It may be some student information or employee information, or it may be anything, but generally for simplicity, in case of demos, we go for some integer data item. This is one field. Then there is a pointer field, which is we generally call it as link, but when we write it in program, we call it as next. So there will be a pointer field. Now the important thing is when you take this pointer field, so this is the node data field. This represents the data. So this represents the data. This is data, but link field should refer the a node of same type. So here the next pointer, this pointer is again the same type of pointer, struct node only. So I had to use struct node asterisk to indicate that every node consists of a pointer which will be pointing to the similar kind of node. So if a structure, part of the structure refers a variable of same type, this kind of structure we call it as self-referential structure. So in linked list, we go for self-referential structure. This is a self-referential structure. This is a common question in interview. What is self-referential structure? Self-referential structure is nothing but there will be a reference within the structure which refers the data item of same type. So this is a type struct node. This is type struct node, and it is referring, it is using a pointer again of type struct node. So this kind of reference is there in structure. It is called as self-referential structure. So the self-referential structure is the one which will be holding a reference. Reference may be a pointer or reference which will be referring to the data item of same type. So this is a self-referential structure. So this is how we represent a structure. But one more point to note here is, normally when I want a node of this is just a structure definition. I want a particular node. I want to create this node. So to create the node, what I have to do is struct node, node1. So I am creating a node of the same type. So when I want to create a node of structure, what I have to do is each time I have to use the keyword struct. So this is each time again I want a pointer to the first node. So I have to say p first or start, something like this. So each time we have to use the keyword struct in order to declare a data item, whether it's an ordinary variable or pointer. So to avoid the usage of keyword struct, generally in data structures, what we do is we use typedef. So typedef struct node, whatever it is, then we'll say int data, then struct node next. This is then this is typedef. What it does is it will replace this entire type. This is actually a type with whatever you are giving here. So node. So I'll name it as some node. Now instead of struct node this each time, now I can declare a a variable of structure, simply node1. So node start. This is how we do it. So typedef is actually defining a new type from existing type. So this is a existing type. From existing type, I'm creating a new type. So once I create the new type, in place of this existing type, I can use the new type. This can be used not only for structure. Generally, it can also be used, like suppose if I say type int, I can say int asterisk, I can say intp. Now in place of int asterisk, I can use intp. So now this is the existing type. This is the new type. This is just for our convenience. To have a convenient programming, we can go for this. Here, to avoid struct, we use it in this kind of situation to have actually a meaningful or suitable name for the data type. We go for typedef. This is typedef. So now in place of int asterisk, I can use intp. So I can also say type def. So unsigned char, I can say uchar. Now in place of unsigned char, I can use a new type uchar. So typedef actually is used to define a new type from existing type. Why to define a new type is to make the programming simple. Here, to eliminate the keyword struct each time we are using typedef. Here, instead of using unsigned char 2 words, I can use one word here. Or suppose if I want to have some integer pointer which will be having some pointer to some data, so I can say data p. So this is actually I'm giving some meaningful and purposeful type name in place of a general name. So this is just for to make the programming convenient. We go for typedef. Even in case of linked list representation, we use structure typedef to define a structure from to define a new structure type from existing type, so that the new word can be used to declare variables of the structure. So this is how we will be representing the linked list in C language. So what we do is here, we'll first we'll write one very simple program to create a node and attach it, then display it. To create a node and attach it and display it. So what I'll do is I'll take a loop here. I'll read a number. I'll read a number, and if some number I'll be reading suppose I'll read number into num. Suppose num whatever user enters I'm reading, and once the user enters -1, I should stop. So first if the user enters 100, I'll take a node with 100, then create a pointer, then I'll take one more next 50 is entered, I'll create 50, I'll attach a link to this. Then suppose 150 entered, I'll create a link, attach this, and suppose if -1 is entered, I'll stop this, and there will be a start present here. Later, I'll display this data items one by one. So I'll take one simple program. I'll use dev C++, which is IDE, open source IDE. So that's why I have downloaded. So what I'll do here is I'll take C program. So I'll create a structure type def struct node int data, then struct node pointer next. So this is how we declare, and as I told you, I'm using the type def to declare the to have a name node, so that from here onwards I can use node capital NODE instead of struct node. So I'll take main. I'll declare a pointer to node. I'll declare a pointer which is start, and I'll assign it to assign null. Then what I'll do is I'll take okay, int num. So I'll take a loop. So I'll take for while true, while 1. I'll take a loop here. What I'll do here is I'll ask the user to enter a number -1 to stop. So as long as it is not -1, I'll keep on proceed. So I'll read it. So if I'll read scanf %d num. So if num equals to -1, I'll stop, break. Otherwise, I'll continue. If it is other than -1, I'll continue. So what I'll do is I'll create a node pointer to node. So here it is always a dynamic memory allocation. So what is there here is as per the logic, I have what I have start. I have, so there is a start. There is a start, which is a pointer to a structure which I'm keeping it as null. Then I'm taking a p node, which does not have any memory allotment. So what I'll do is now I'll create once I read a number. I'll read a number. So suppose num is entered as 100, whatever it is. Now what I'll do is I'll create a node, allot memory area for node. Suppose what I'll do here is I'll take p node. I'll allot memory area here. Node pointer is type casting. So I'll say malloc size of struct node. size of struct node. So I'm allotting memory area for a node and it is a pointer. I'm allotting a node there. So a node is allotted with data on next allotted here. This is some memory is allotted and the address. This is suppose assume that this is 1000 because it is dynamic memory allocation. 1000 is stored here. Now it is pointing to this. Now what I'll do is after allotment, I'll move 100 here. I'll move 100. So when I move 100 here, so memory is allotted. Now I'll say P node. And whenever it is a structure, I have to use this form data equals to num. Now I have to, because this is the first node. This is the first node. What I have to do is I'll also link this address. I'll also copy into this. So how I know it is first node? When this is null, I'll copy this into this. So this is 1000. So here what I'll do is if start equals to null, that means when it will be null, when it is first node. Start equals to null, then what I'll do is I'll say start equals to P node. Start equals to P node. So if it is first node, I'll say start equals to P node like this. Now, if it is so, then this is 1000 and this is created here. This is pointing to this. Next time, again, I'll do this. Suppose if it is 50. So what I'll do is if it is 50, another node I'm creating, 50. Now, because the new node created will be pointed by P node. Suppose assume that this is 2000. So this is pointed here. This is pointing to this. Now I'll insert this in between these two. When it is not first node, I'll insert this in between these two. Now this is P node pointing to this. Now to insert this in between these two, what I have to do is this 1000 I should store here. So 1000, the address whatever present I should store here. So 1000 I should store here. Then this address I should copy into this. Now this is pointing to this and this is 1000, it is pointing to this. So if it is not first node, what I'll do is I'll say what I'll do here is P node next. P node next. That means into this P node next, I'm storing the starting address equals to start. This what I'll do is I'll say else. If it is not first node, I'll do this step. Do this step. Then I'll say start equals to P node. Because start equals to P node is always there. So what I'll do is if it is not null, so the better logic. So I'm reducing the code. If it is not null means if it is not first node, what I'll do start, even if it is first node, I can do this. So I think whether it is first node or not, I'll do this one only. So this is better. P node next equals to start equals to P node. So these steps are necessary. So I'll do it again to avoid confusion. So what I'll do is I'm fine tuning the program parallelly. So what I am doing here, I'll make you understand. So what I am doing, I have a start. Start is null. Then I have a P node. I am not assigning anything because new node will be used there. Now I'm reading num. Assume that it is 100. So when it is 100, so I'm creating a new node with 100. And assume that this is 1000 address. So when it is 1000 address, what I'm doing, I'm copying 100 here. This 100 I'm copying here. Then P node next equals to start. P node, that means once I say malloc, Once I say malloc, this node is not only created, but also this address is stored here. So 1000 is stored. So this is what happening after malloc. Then I'm saying p node data, this 100 I'm copying here. The next step is p node data, 100 I'm copying here. Then p node next equals to start. P node next is this one. So what is start? It is null. So last node should be null. Next, what I'm doing, start equals to p node. Start equals to p node means this is 1000. Now this will also be pointing to this. This is the status in the beginning. Next, I'm again repeating the loop. Assume that now it is 50. When it is 50 again, it is not -1. I'm alerting memory area. So when I alert memory area, a node is created. Node is created with some address 2000, and that 2000 is copied here because we are saying p noding. Now this is no more a link. This is pointing to this. This is pointing to this. Then p node data, this part we are storing 50. We're storing 50. This is after this two steps. Next, what we are doing, p node next. What is p node next? This part, what I am storing, start. What is there in start? 1000. So when I copy 1000 here, what happens is this will be pointing to this. Now, next start equals to p node. What is p node? 2000. So now start is no more pointing to this. There is a 2000. That means start is pointing to this. Now, when I start from here, it is pointing to 2000. From here, I'm going to 1000. Then from there, I'm stopping null. So this is how the construction proceeds. Again, I'm creating another node. Assume that now I'm storing 75. So I'm reading 75, which is not -1. Then I'm creating a new node again. I'm dynamically alerting memory area. So 75, assume that this is 2400. The address is 2400. Now 2400 is stored here. Now this is pointing to this. Now next step, what I'm doing, p node next equals to start. Into this, what I'm storing, 2000 I'm storing. When I store 2000 here, this is pointing to this. Next time, what I'm doing, start equals to p node. So 2400 I'm storing here. Now this is pointing to this. Now if I start from here, assume that I'm starting from here where 2400 is there. So I'm reaching here. 2400. From 2400, I'm taking 2000 and reaching here. From 2000, I'm taking 1000 and reaching here. From 1000, I have null. I can stop. So this is how the logic proceed. So once I enter -1 here, the construction will be stopped, and the building of linked list will be stopped. So I have built the linked list with some nodes. So this is how it is built. Now I can traverse through the nodes, all nodes. So what I'll do is I'll take, if I want to traverse through the nodes, I should not disturb the start. Start should be always pointing to the first node. So I'll use same p node equals to start. This is this part of the loop. What it is doing is this part of the loop is building a linked list. Building a linked list. Now, once I build the linked list, I want to traverse. So this is traverse. So traversal is the basic operation in data structure where we'll be visiting each and every node of a data structure one and only once. This is traversal part. So traversal, what I have to do is I have to run through all the nodes. So to run through all the nodes, what I have to do is first take the starting node in the pointer. Then now when now this is the setup. To be clear, what I'll do is I'll read out this diagram in a neat way. So this is how internally it is present. For our convenience of understanding, what I'll do is I'll take the first node. I'll take the first node. I'll take the second node. This is for our understanding. I'm rewriting the diagram, redrawing the diagram. So this is 100. This is null. And the address of this is 1000. And 1000 is stored here. So when 1000 is stored here, this is linked to this. Then this one is 50. and the address of this is 2000. Then this is 2000, so this is pointing to this. Address of this is 2400, and this is 75, and the start is the node which is pointing to this. So this is just for convenient of understanding this entire diagram. I'm redrawing this way. Now what I had to do is I had to traverse. Traversal is the technique in data structure which is used to visit each and every node one and only once to do some kind of processing. The kind of processing what I want is display. So to display what I had to do, first I had to visit here and display 75, then go here, display 50, go here, display 100. Now there is nothing, after that. So I had to stop because it is null, I had to stop. Now start will be always pointing to this. I should not disturb because once this start is disturbed and not pointing to this, then I cannot come back here. So what I had to do is when I have to traverse, I had to take one more pointer, which the same pointer which I'm using to create, I'll use. So what I'll do is I'll store first start into this. When I store start into this, that's what I'm doing. This will be pointing to this. Now I had to keep on move through the linked list till P node becomes. So initially P node is 2400, then it becomes 2000 because 2000 is available here. It becomes 2000, then it becomes 1000, then it becomes null. So as long as P node is not null, I have to proceed. So I'll say P node not equals to null. P node not equals to null. I have to proceed. So what I have to do, I'll say printf percentage D. I'll use this arrow just to indicate this, then percentage D. So I'll say P node data. P node data. So I'm printing this. Then I have printed this. Now P node data means 75 is printed. Now I should move P node point to this. How to move P node to point to this is P node equals to P node next. So when I say P node equals to P node next, so P node next is 2000, P node next is 2000, 2000 is copied here. When 2000 is copied here, what happens? This will be pointing to this. So it is pointing to the second node. Then I'm printing 50, then P node next is 1000, 1000 is copied here. Then this is no more pointing to this, this is pointing to this. Then I'm printing 100, then P node next is null, null is copied here. And now when it is null, what I am doing, I am stopping. So this is the logic for traversal. So this is the program for building, and it is a simple program to insert a node into the linked list, that too in the beginning. Then it will be, we will also be doing traversal. So when I execute this, so this is simple linked list. I'll say simple list dot C. So there is a semicolon missing here. So I'll execute it again. So enter a number. So I'll use the same numbers. So first I'll enter 100, then I'll enter 50, then I'll enter 75. So 100 I'll enter, then again 50, then again 75. Now I want to stop. To stop, I'll enter -1. So it is printing 75, 50, 100. So that's what we want. So it is printing 75, 50, 100. This is how the linked list is built. This is one simple option here. I'm building the linked list by inserting new node in the beginning, then I am going for traversal. So this is how we can build a simple linked list and traverse through all the nodes. So this is one simple program. So normally when I take any data structure, so here I have explained already logic. So I'll proceed with the next concept. So next, when I take these, normally I should have given this earlier. Now I'll give it. So data structure operations. So normally when you take any data structure, we do insert, means add a data item into the data structure, insert. The second one is delete. We have to delete a data item. Third one is traverse. These are the common operation, traverse. Fourth operation is search for a particular item, whether it is present or not. Fifth operation is normally these are the basic operations are these three. Then search is also there, and search is also there, but mainly insert, delete, and traverse. Then finally sort. But sort is not applicable always. Sort is based on the requirement we apply. So insert, what we do is add a data item to the data structure, add a data item to the data structure, like what I am doing already in this program. Now this is a remove data item, from the data structure, and traversal is a technique. What we do is visit each and every item, each and every node of data structure one and only once. So we have to visit each node one and only once. So that is traversal. Now search is check whether a particular item is present or not. Check whether a particular item is present or not. Then when I take sort is to arrange the data items in order. Normally in linked list, we do sorting very rarely, so we are not going to see that sorting here. Now we have already written the logic for traversal. We have written logic for insert. So traversal is visiting each and every node one and only once. So that this is the traversal logic. So the simple traversal logic is we take the starting address and run through the remaining nodes. So that is this is traversal. Now here we are inserting, but it is only one type of insertion. Now we'll see much about insertion here. So when you take a linked list, so we insert. So there is already a linked list. Assume that there is a linked list present like this. So assume that there is a linked list present like this. So there is suppose 10, 15, 5. These are the data items present. This is start. This is existing linked list. And last item pointer will be null, and this will be pointing to this, and this will be pointing to this. Normally what we are doing is we are inserting new data here in the program. We are inserting here new data in the beginning. So whatever we have done here, now insertion can be of any time in this linked list. Insert in the beginning. So to insert in the beginning, this is the logic. So what I am doing, I am creating a node, and starting address I have to store in the new node link, and starting address should be modified to new node. This is insert in the at the beginning of the linked list. This we have already done. Next is insert at the end of the linked list. So insert at the end of the linked list. That means here, so insert beginning means do here, this should be linked here and this should be linked here. Insert at the end means create a node here. This should be pointing to this and this should be null. This is insert at the end. This may be, I may be inserting 100 here. I may be inserting 50 here. So this is another kind of insert. Third kind of insert is insert after a given item. After a given item. Now I want to insert a new node. I want to insert new node 60 after 15. So when I want to insert 60 after 15, I have to go here, then copy this point, make this point to this and make this point to this. So this is insert after given item. So there are three kinds of inserts that are possible. I have taken only one, which is insert at the beginning. We can also have insert at the end, and we can also have insert after given item. So these are the different kinds of inserts that are possible in case of linked lists. But here I've taken care of only one kind of insert. This is another activity we can do. So when we take this linked list, so we'll next write all possibilities of inserts. So add item to the data structure, but wherever it is possible, if the user wants it to insert at the beginning, I have to insert at the beginning. If the user wants it at the end, we have to insert at the end, or wherever it is required, we have to insert. So that will write it. Next, we'll see the delete operation. When you take the delete operation, so I'll take a linked list, again, some linked list. So this is assume that this is 10, this is start, and assume that this is 5, assume that this is 15, assume that this is 25. This is not. Now I may have to delete 5. I have to delete 5. So what I have to do is, when I have to delete 5, so I should bypass this node. So to bypass this node, what I have to do is I should store address of this node. Suppose assume that this is 1000, this is 1200, this is 1400, this is suppose 1800. So 1400 will be present here. Then 1000 will be present here, 1200 will be present here. Now, if I want to delete 5 from this, what I have to do is, now this 1000 I have to copy here. When I copy 1000 here, now this link is removed. This link is removed. So when I start, I'm bypassing this node and reaching here. And once I'll remove this link, I can delete this node. So then delete this node. Delete the node. How to delete? By using free function. So I can use free function and delete this node. So whatever that node, we have to delete. So this is how we delete. So we'll write even this option. We'll write the part of the program. What we do is, for every operation, we will take a separate function. For insert at the beginning, we'll take a function. For insert at the end, we'll take a function. Insert after a given node will take a function. Delete a given node will take a function. So this is how we. This is another operation. What normally we do it. Next is a search operation. Now, when you take any kind of operation, it will not be so simple. So if I take 5, I may be asking the user to delete 5. So 5 will be here. I may bypass. Now, suppose if I delete 10. So now when I delete 10, then there is no further node present. I have to consider this as a special case. So whenever you write the logic, so sometimes you have to write a general logic which is applicable for all nodes, almost all nodes. Sometimes you have to take some special cases. So sometimes this is general logic applicable to all the nodes. almost all applicable, all nodes. Now, so write the logic which is applicable to all nodes, but check whether for some special cases it is working. Like suppose in the deletion, I may be deleting some node, so it is working fine. Suppose one special case what I have to consider here is, special case is first node if I am deleting, whether this logic is working fine. If it is working fine, then it's okay. Otherwise, you have to write a different logic to delete first node. So always your thinking should be like that. So whenever you write a logic, sometimes you have to take some special cases. So that logic, whatever you write, may not be working for all cases. So if it is not working for all cases, take case by case. So first node, whether it is working fine. If it is working fine, okay. Otherwise, write a different logic. Similarly, so whenever you write a data structure program, these considerations you have to make, because sometimes some special cases it may be failing. So next you check whether if I delete last node, whether the logic whatever I have written is working fine or not. If it is working fine, it's okay. Otherwise, we have to consider slightly different logic, which will be suitable for that particular special case. So this you have to keep in mind always, whatever type of data structure program you are writing. So you have to always keep in mind. So we'll be considering each time the special cases. Even here, suppose if I had to delete at the after a given node. So I want to insert after a given node. So I'm saying insert after 15. So it is working fine. It will work fine. Now suppose there is a 10, there is 15, there is 60, there is 100 here. Now if I want to insert after, I'm asking to insert after 80. 80 is not there. Then what is going to happen? So if it is not there, whatever node I'm referring not there, check whether the general logic is working fine or not. Otherwise, consider it as a special case. Suppose if the node what I am referring is a last node. So after 100 I am to insert, what is going to happen? So if the node after which I have to insert is the first node, whether it is working fine or not. If it is not there, whether it is working fine or not. So data structure programs, for every kind of operation you perform, some special cases you have to consider. Otherwise, the program will fail. So we'll be seeing those kind of logics. So you carefully observe the logic, whatever I'm writing, and try to follow, and you have to practice, because when you take this data structure program, logic will be slightly complex. And one more thing what you can do while you develop the data structure programs is always take this kind of diagrams. So when you take this kind of diagrams, so it is take, if I want to insert a node, what I have to do, take the diagram. So if you write the diagram, logic will be somewhat simple. So building the logic will not be simple, but building the logic will be simple when you take a diagram and do the same operation. So whenever you write data structure programs, two things you have to consider. One is the special cases. I have given the different possibility of special cases. Second thing is, suppose if you feel there is a confusion in the logic, ambiguity, then go for a diagram, this kind of diagram. When you go for a diagram, then the logic building will be relatively simple. So this is one more thing. Next, when you take the one more operation with the linked list is search. So search operation is actually very simple. Suppose if I have a linked list like this, assume that this is the linked list. Assume that this is the linked list 50, 10, 15, 65. So when I want to check whether a given node is present or not, then I have to keep on start from the first node, check whether it is matching. If matching, stop, otherwise go to the next node. So you have to keep on match the data with the given search value. which generally we call it as a key. So the search item will be called as a key. Now key, there will be suppose 25. So 25, whether it is matching, not matching, then go to the next node. It is not matching, go to the next node, and so on. So till a match is found, you have to proceed, or till you reach the end of the linked list, you have to proceed. Once a match is found, you can stop and say the search is successful, and display the details of the node which you found. Suppose if search is when you reach the end of the linked list without success, then the search the node whatever you are trying to search is not available